We've mentioned IPv6 a few times, and we've mentioned how our current version of IP addressing is IPv4. Well, what is the difference between our IPv4 and IPv6, and what's the format of our IPv4 versus our IPv6? Well, our IPv4 is a 32-bit address scheme, meaning we have 32 binary bits of data, 32 ones or zeros of data. These 32 bits of data are divided into 4 octets. So we are dividing our 32 bits into 4 sets of 8. Now this leaves us with 4 billion addresses. Our IP addresses typically look like 192.168.1. whatever. And then we have IP addresses which look similar to 11 0.0000000001.000000001. Extra 0 there. There we go. So that's what our IPv4 addresses look like in binary. And this provides us with 4 billion addresses. Now, at the invention of IPv4, this seemed like more than enough addresses that we would ever need. But fast forward to the year 2014, and everyone has phones. Everyone has tablets. Everyone has computers. Everyone has, well, not everyone, but some people have refrigerators that connect to the internet. Give it a couple years, everybody will have a refrigerator that connects to the internet. It'll be so old-fashioned. But all of these devices connect to the internet. All of these devices need IP addresses, and we're running out, simply put. We need something that provides us with more. We need something with more extensibility. We need something with more numbers. We need something with more binary addresses. We can only get so many addresses out of a 32-bit address. So IPv6 provides us with a 128-bit address. A 128-bit address is an address that it doesn't have four sets of 8 binary digits. Our 128-bit addresses provide us with 128 binary digits, which I'm sorry, but I'm not going to write out because that would take a long time. But 128 binary digits provide us with 340 trillion addresses. That's a lot more than 4 billion. So it's going to provide us with addresses for years to come, for the foreseeable future. But there's a little bit of a difference when it comes to our format. Our IPv4 is a 4-octet dotted decimal 32-bit address. Our IPv6 is in hexadecimal format. So we don't have periods that separate our sections, and it's hexadecimal, which means our characters can be anywhere from 0 through F. Well, how can we have letters? How do we have 0 through F? Well, the trick is every single one of our characters is actually composed of 4 binary digits. It's amazing. So let's take a look at FE01 and see how that can be composed into binary. So let's take a look at that over on our other side. So FE01. And remember, this is just one section of our IPv6 address. FE01. When we break this down into binary, this is going to be 4 groups of 4 binary digits. So when we're looking at our binary digits we'll go ahead and write out a chart again. Binary digits work in incremental powers of 2. So if we have 4 digits, say 1, on, which we'll actually write in black, we have on, and then these will be our binary places. So these are the binary digits which represent our each individual character here. So each of these digits have a value, or each of our places have a value. We have a 1's value, 2, 4, and 8. Now you say, well, why can't we just use numbers if we only have up to 8 in our value? Well, when we add these up, for example, if we have every single binary digit activated in our set of 4, 1, 1, 1, 1 will be 8 plus 4 plus 2 plus 1. Well, that's going to give us 15. We can't put 15 in our hexadecimal format because that may cause confusion. Is this a 1 and a 5, or is this a 15, or what? Is the number, if the number before it is a 1, is it an 11, is it a 15, or is it a 1, 1, 5? So we have to limit ourselves to 0 through 9 for our numbers. But luckily, we also have letters. So our chart here, we'll make one right here. If we have a value, if we have a binary value which comes out to 1, so a binary value of 1, then the hexadecimal character that we will place will be, well, we'll start 1 down. If we have a binary value which comes out to 0, our hexadecimal that we place, it will be 0. If a binary value comes out to 1, the hexadecimal character will be 1. Then on to 2, 3, 4, 5, 6, 7, 8, 9. These all correspond directly to their corresponding numbers. Binary value in red corresponding to the hexadecimal output in green. We may run out though. We ran out of numbers at 9, so if we have a binary value of 10, binary value of 10 is a hexadecimal value of A. Binary value of 11, 12, 13, 14, 15 will also need hexadecimal value of 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. That's why our hexadecimal characters, that's why in our IPv6 we can have characters that are anywhere from 0 to F, F being the highest hexadecimal value. So let's go back to our chunk of binary that we pull, or our chunk of hexadecimal that we pulled from our IPv6 here. We have our IPv6 value of FE01. So FE01, F is going to be a binary of 1111. So binary of 1111. E is going to be 1 less. So E will be 14 and will be a binary value of 1110. 0 is going to be a binary value of 0000. And then lastly, 1 is going to be a binary value of 0001. So we can see how even with our IPv6 address being long in hexadecimal format, we are exponentially making this address even larger when we go into binary format. Each of our hexadecimal segments of 4 characters equals 16 binary digits. Our entire address, our entire IPv6 address is 32 hexadecimal characters long. 32 hexadecimal characters times 4 binary digits per hexadecimal character results in our 128-bit address. So that's how we get that 128-bit address. That's how we use hexadecimal and convert binary to hexadecimal and hexadecimal to binary, using our 1, 2, 4, 8, and then realizing that once we hit 9, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Now we have this long IPv6 address. And the makers of IPv6 recognized that it's going to take a long time to get used to this, and it's going to be very difficult to write out this address like this every time. So they gave us a little bit of help in that they gave us some rules that can help shorten this address. with our IPv6 address, we can get rid of consecutive zeros one time by the use of a double colon, like this. Now, the reason we can only use this double colon once is because this double colon, in order for our computer to find out how many zeros we're replacing with this double colon, takes however many other digits that we have in our IPv6 address, takes all those other digits and says, okay, I know I have 32 hexadecimal digits total. I have 28 that I can see. That means that I'm missing 4 zeros. That must be what this double is replacing. It's replacing 4 zeros. But if we did this in multiple points, if we put a double colon in multiple points, our computer won't be able to tell, it'll be impossible to tell how many sets of zeros each colon replaces. If we use a double colon twice in our address at different points and we're missing 4 zeros, is it 2 zeros for this and 6 for this one, or is it 4 here and 4 here, or we don't know. So our double colon we can only use once, and typically we'd want to use this in the place where it would save us the most amount of zero writing. So we have our address here, and we notice the most consecutive sets of zeros we have is right here at the end. So we'll just take all of these zeros and replace them with a double colon at the end. Now we can also omit leading zeros. So our 0DB8, we can omit that 0. And our computer knows that, okay, I'm missing a character here in this set of 4. It must be a 0 because the only reason I'd be missing a character here is if it was a leading 0. So we can omit leading zeros. And then again, we can replace clusters of zeros with that double hyphen. So by using these tips, we can reduce our IPv6 address by a little bit, but it's still a long address, and it's still going to be a system that we're going to have to get used to in the future. But as for now, we're still using IPv4 mainly with our 4 octets, our 32-bit dotted decimal format. So just as a quick wrap-up of our IPv4 versus our IPv6, we want to remember that our IPv4 is going to be a 32-bit dotted decimal address with 4 octets of 8 binary digits in each octet, and this gives us 4 billion addresses. Our IPv6 is going to be a 128-bit address, which gives us 340 trillion IP addresses. It's going to be a hexadecimal address with 32 characters hexadecimal, each character represented by 4 binary digits. In each of our hexadecimal sections, we have a couple of rules. We can only use 0 through F because that's the way that hexadecimal works. Consecutive zeros can be replaced by a set of double colons one time. So if we have a string of consecutive zeros, no matter how long they are, as long as they're consecutive, and as long as we only replace replace a string of zeros using a double colon once, we can do that. We can replace our longest string of zeros with those double colons. And then lastly, we can omit leading zeros in sections. So if we have a leading 0 in a hexadecimal set between 2 colons, we can omit those leading zeros and our computer will automatically add them back in. So by recognizing our differences between our IPv4 and IPv6, we'll be able to be a little bit more ready for the transition to IPv6. We'll understand how our computers address using IPv6, and we'll understand how to make these long addresses a little bit shorter.